Okay, so the next thing that we would like to find is how do we find the volume of a solid? Okay, so we are going to do this means use section 6.2 and 6.3 to introduce the technique. And then to me, I will separate into three parts. The first part is how we find the volume by sliding. And the second part is how we find the volume by rotating. And then the last one is in section 6.3 is actually how do we actually find the volume by using the shell method. Okay, so therefore again, you will see that I have 6.2a, which is related to finding the volume by sliding. 6.2b is actually finding the volume by rotating. Okay, we actually record we are using this method. Okay, and then in 6.3 we are going to use the shell method now. Okay, so then maybe let us begin. How do we actually find the volume? Okay, by sliding. Okay, now first of all, if we actually we have a solid. Okay, how do we actually find the volume of a solid? The idea is we would like to use the base area multiplied to height, right? This is the idea. How do we find a solid? Okay, the volume of a solid. However, you will see that most of the solid that if you look at the base area, okay, the bottom and the top, they actually they have different that's mean what area. How do we actually find the volume of a solid then? Okay, now in this case, what we are going to do here is we would like to cut the solid, okay, perpendicular to the base. Okay, we would like to cut it really small. Okay, that's mean a slide right here, right? And then you will see that to each slide, you will have the base area. Okay, they are really close. The top and the bottom, they're really close. And then the height here, we will make it really, really small. Okay, then after we slide it, and then what happened? We are going to add them together. Okay, slide by slide, and then to make it the total solid. Okay, so this is actually is the idea about this method right here. Okay, so then let us look at how do we do it in math now. Okay, so first of all, if we have a solid S right here, what we are going to do is we are going to divide this into a really thin horizontal line right here. Okay, just cut it. And then to each slide, you will see that we have a height is a delta y. And then you will see that what happened to the base area. The base area is, and the top and the bottom, because we cut it really, really thin. So therefore, the top area and the bottom area is really almost the same, right? It's kind of like what we have a solid like this, okay? Then we will be able to find the volume of each slide right here. Then the volume of this line right here, for example, if I cut it to this one right here, then you will see that we will have the base area is the area of I minus 1, okay, times the height, the delta y in this case, okay. And then you will see that each line is nearly a right cylinder, which whose volume can be approximately has the area times height. Okay, just like this. Okay. And then suppose that that solid body extended from the height is y equal to a to b along the y-axis, and then let a sub y be the area of the horizontal cross sections, just like this right here, or maybe I could have this one right here, okay? And to compute the volume of V of the body S, that's mean this whole thing right here, then we divide S into N horizontal line of the thickness of delta y equal to b minus a over n, okay, then this is actually is my delta x, delta y now. Then the volume of each slide will be v sub I is a of the, this is the base, okay, this is the slide of y minus 1 here, okay. Then this area right here is what we have is a of y sub I minus 1 here, and time delta y then, okay. And then now what we want to do is we add them together. We add all the small slides, okay, the thin slides together to make the solid. If n go to infinity, meaning what delta y is getting closer and closer to 0, okay, then this is actually is kind of like the idea what we have in section 5, right? So we could actually take the integrations from a to b of a sub y dy. What is a sub y? A sub y is the cost, the area of the cross sections. Okay, so this is actually is the idea about this section right here. Okay, so the volume has the integral of the cross section area. Then let a sub y be the area of the horizontal cross sections at height y of a solid body extending from y equal to a to b to y equal to b. Then the volume of the solid is integrate between a to b of a of y. Now remember, a of y is the area of the cross sections, okay, dy. Okay. However, what if I want to cut it like this one right here is perpendicular to the x-axis, okay? Then in this case right here, then we could have the volume is equal to integrate between a to b, from a to b, right? Of a of x. A of x is the area of the cross sections, like this one right here at the x then. Okay. Okay, so it depends on how you cut your solid. You could cut it perpendicular to the y-axis, or you could cut it perpendicular to the x-axis then. If you cut it perpendicular to y-axis, then you work with dy. If you cut it perpendicular to the x-axis, then you work with dx then, okay? Yeah, just like this. Okay, so right now, I would like to show that how do we find the volume of a sphere of radius r is v equal to 4/3 pi r squared, okay? So what we are going to do here is, again, now if we have a sphere, okay, we know that in this case right here, from the center, this is actually is r, right? Okay, now what I'm going to do here is I would like to set up a coordinate system. So this is x, this is y right here. Okay, now you will see that now I would like to cut it perpendicular to x-axis, meaning I would like to cut it this way. Okay, now you will see that if I cut it right here, then what happened to the cross sections? The cross section is basically, it's just a circle, isn't it? Okay. Now, if you cut it right here, okay, then of course your cross sections is actually, again, is still a circle, right? No matter how you cut it, then the cross sections is always a circle then. If you, okay, if you understand this, then this is, which is great. Okay. Okay, so now in this case right here, that's mean what I'm going to do here is, of course, if this is, that's mean I will integrate between negative r to r. Okay, so I would like to set it up. So the volume to this one right here is actually, it will be set it up between negative r to r. And then now what I'm going to do here is, because I cut it perpendicular to the x-axis, so meaning what I would like to find the area of the cross sections dx then, okay, a of x dx. Then now, what is a of x? Now remember again, a of x is the area of the cross sections. Okay. Okay. Now, one thing that we know, if this is xy here, okay, then of course I will be able to corresponding to this is the y right here then. Okay. So therefore, in this case, what is the radius of this xy here? It will be y. Okay. So then in this case, the volume that I have is actually is negative r to r of pi y square dx then. Okay. Because again, this is the cross section area right here. Okay. It's pi y squared. Okay. But one thing that we know, if we want to work with dx, meaning what? I need to have y in terms of x now. Okay. Then how do we actually work with y in terms of x? Okay. So then now let us pay attention to this. Do you see that right here? We have a right triangle, right? This is x, this is y, this is r right here. Okay. Then we know the r values because we would the radius is r. Okay. Then now we know that in this case I have x squared plus y squared equal to r squared. Okay. What I would like to have is I would like to have y depend on x. So basically what I could do here is I could actually solve for y then. So I will have y squared is equal to r squared minus x squared. And then to this one right here, I have y is the square root of r squared minus x squared then. Okay. Okay. Then if we know this, then now what we could do is we could change the y square into pi times r squared minus x squared dx now. Okay. Okay. So again, remember y squared is equal to r squared minus x squared. Okay. And then of course we know that pi is just a constant. Okay. Now we could actually integrate this. So I have pi, and then I will have r to the power 3 over 3. Oh, my bad. Remember r is a constant. So I have r squared x minus x to the power 3 over 3. And then integrate between negative r to r. Then now, do you see that what happened is the integration between negative r to 0 and from 0 to r, they are the same, right? So what we could do here is we could change this one to 2 pi integrate between r squared x minus x to the power 3 over 3. We integrate between 0 and r then. So we could do that. And then now, what we could do is we could finish the problem now. So it will be 2 pi. And then now I will have r squared of r minus r to the power 3 over 3 minus 0, right? So I will have r to the power 3 minus r to the power 3 over 3. So you will see that the volume of a sphere is 4/3 pi r cubed then. Okay. Okay. Then now, the next problem is I would like to find the volume of this object right here. Okay. Now, of course, you will see that the volume of this one basically is the base area multiplied to height. Okay. So therefore, in this case right here, we know that the base area is actually 6 times 4. So meaning what the volume is equal to 24. Of course, right now, what we want to do here is we would like to use a calculus to find the volume of this object right here. Okay. I would like to approach it into 3 ways. One is perpendicular to the x-axis. Another one is perpendicular to the y-axis. And then the last one is perpendicular to the z-axis. Okay. So how do we actually do this? Okay. So now again, remember we know the answer already. The volume must be 24. Okay. Okay. Then let's see. How do we actually work it out this problem? Okay. So to me, what I would like to do is I would like to, again, try to sketch the graph. Okay, so this is the x-axis. This is, okay, so basically we just concentrate on the x-axis. Okay, now if we want to cut this perpendicular to the x-axis, then what happened here is we would like to have the area, okay, of the cross sections basically is something like this, isn't it? Okay. Then now what we want to do here is I would like to find this, maybe I call this a sub x right here now. Okay. Okay, this is okay. Okay. Then, of course, in this case right here, okay, how do we actually set up the volume here? Okay, so we know that we would like to integrate between 0 and 6. Okay, and then now I will have a of x dx. Okay, so how do we find a of x? Okay, so in this case right here, now if we want to take a look of this right here, then we know that to this one right here, we will have 4 right here, and then this is 2. Okay. Okay. Then if I say that this is a right here, of course, the cost area will be 4 times a then, right? 4a. Okay. But one thing about this is how do we actually find a depend on x now? Because again, I would like to have everything depend on x. Then now let us look at the, okay, so here is my a. And then I know that this is 2 right here. This is 6 right here. Okay. And then remember, x is right here. Okay. Then now, how do we actually set up? Again, you will see that this is basically the similar triangles. Then we know that this from here to here is 6 minus x. Okay. So now, basically, I will have a over 6 minus x is equal to 2 over 6. Then, of course, to this one, we know that a is x minus 6 over 3 then, right? Mm-hmm. because this is 1/3 right here. Okay. Then now the whole problem become a little bit easier to work now. So you will see that the a of x, the area of the cross sections, basically is 4 times 6 minus x over 3 dx. Okay, so we have everything depend on x. Okay, then now, so maybe I could do this. So I will have 4 over 3, take it out, integrate between 0 and 6 of 6 minus x dx now. Okay. Then now I will have this is 6x minus x squared over 2, integrate between 0 and 6. Okay. Then I will have 6 times 6 minus 6 squared over 2. So I will have 4 times 18 over 3. Then we know that the answer is 24. Wow. This is what we are looking for. Okay. Okay. Then now it is your turn. I would like you to actually think about this. Okay. Try to work on B and C. Again, think of how do you slide it. Okay. Okay. So now the next one right here is I would like to make it perpendicular to the y-axis. So therefore, in this case, you will see that this is my a of y. Okay, so we will integrate. Let me have those labeled first. This is 4, this is 2, this is 6 right here. Okay. Okay, now to this one right here, I would like to find the area, the volume. Okay, so perpendicular to the y-axis. So then in this case, you will see that to the y, we have it from 0 to 4. And then of course I will have a of y dy then, right? Okay, but one thing about this is, now you will see that the cross sections, the area of the cross section basically is all the same. This is 2, this is 6 right here, okay? So therefore you will see that a of y basically is 1/2 base times height, okay? So which is equal to 6. So then this become a little bit easy now. So I will have between 0 and 4 of 6 dy, okay? Then now I will have 6y integrate between 0 and 4. Of course, in this case, I will have 24 then, okay? Okay, now the last one is actually perpendicular to the z now, okay? So again, let us draw this out. This is z, this is y, this is x right here. Okay, now you will see that if I want to cut it perpendicular to z, that's mean what the cross section that we have. Okay, so this is a of z right here. And then of course, again, this is 2, this is 6, this is 4 right here. Okay, so the volume right here is, we integrate between 0 and 2. of A of Z dz now, okay? Okay, so again, if we say that this length right here is A, then let's take a look. So this is A of Z right here. Okay, so if this is A, this is 4 right here. Okay, okay. One thing about this is we would work with this triangle again, okay? Because in this case right here, this is my A right here, okay? So we know that this is 6 right here, this is 2 right here, okay? And then now, the Z is actually what is from 0, so this right here is Z, okay? And of course, then now we need to work with the ratio now. And from here to here, it will be 2 minus Z, okay? Okay. The ratio here, it will be A to 2 minus Z equal to 6 over 2, okay? So then I will have A is 3 times 2 minus Z now, okay? Okay. Then to this one right here, I will integrate between 0 and 2, and then it's 4A, right? dz. And again, I would like to have A depend on Z. So integrate between 0 and 2 of 4 times 3 times 2 minus Z dz. Okay. And of course, in this case, we could take out the 12. Okay. So I will have 2Z minus Z squared over 2, integrate between 0 and 2. So 2 times 2 minus 2 square over 2. Okay. So I will have 12, 4 minus 2, so it is 24. Okay, so then now, so if you have the same solid, it doesn't matter which way that you cut, right? Cut it perpendicular to X, to Y, or to Z, you will get the same result, okay? Of course, when you analyze it, it is a slightly different way to analyze it then. Okay, so then now the next problem is actually a little bit harder than this one, but again, let's try to see if you know how to do this one. Okay, so right now to this one, I would like to find the volume of the ridges in the figures by setting the area of a vertical cross sections right here. Okay. Okay, so how do we actually work it out this problem? Okay. Okay. Then to this one right here. Now you will see that what happened to the cross section right here. I know that the cross section is actually a rectangle. Okay. So to this rectangle right here, we have A and B right here. Now again, remember A and B, they always change. Okay. Okay, so how do we actually work it out this problem now? Okay. And let's see how do we actually set it up. Now remember, if this is the x value right here, then basically what we want to do is we would like to set up the volume is integrate between 0 and 8, a of x dx. Okay. And now, what is a of x? Basically, in this case right here, a of x is 1/2 base times height dx. Okay, it actually is again b times a divided by 2, right? But because we need to integrate depend on x, meaning what? I need to find the expression that b is depend on x and a is depend on x. Okay, so let's see if we could do this. So then now let us look at a first. Okay, so to a, we could actually work with this triangle right here. To this triangle, I know that this height right here is 4, and then this is 8, and then here, this is my a. Okay. Then now, from here to here, okay, so it's from 0 right here, right? So from here to here is x. Then of course, from here to here will be x, h minus x then. Then now I could have a over 8 minus x is equal to 4 over 8. So meaning a is 1/2 8 minus x then. Okay. Well, then I actually found a. Similarly to b. Okay. So if this is maybe let me use different color. So if this is b right here, okay, then now I need to work with this triangle right here. So this is 6, this is 8 right here, and then of course this is b. Okay, and again we know that from here to here is x, and then from here to here is h minus x. So I will have b over h minus x is equal to, let me see, b over this is 6 over 8 then. So I will have b is 3 over 4 times 8 minus x. Okay. Okay, so then now let us plug it in here. So I will have 1/2. A is 1/2 h minus x. B is 3/4 h minus x. Okay, dx. Okay. Then now I will have 1/2 times 1/2 times 3/4 integrated h minus x to the square. Okay, now you know that we don't want to work with the square, then what we have here is 3 over 16. Okay, integrate between 0 and 8 of 64 minus 16x plus x squared. Okay. Then now the rest of the problem is a little bit easy now. Oh. 64x minus 16x squared over 2 plus x to the power 3 over 3, integrate between 0 and 8. Okay. Okay, so 64 times 8 minus 16 8 squared over 2 plus h to the power 3 over 3. Okay. Then now what we could do is we could actually maybe use calculator, right? Then we found out that the answer that we have is 32 then. Okay, so then this is it, right? So this is actually is the idea about how do we find the volume by sliding, okay? The cross-section area. Okay, so the next section is 6.2b, then is talking about how do we find the volume by rotating. Okay, so this is something that I will talk about this in the next video then. Okay, bye-bye.